Okay, in this video, we're going to look at a probability in a particular situation where we are rolling 3 die. Um, the situation is you roll a fair die 3 times and you need to compute the following probabilities. First, we want to see what the probability is that you roll all ones. What about if you roll all odd numbers? What about if what's the probability that none of your rolls gets a number divisible by 3? What's the probability that you roll at least 1/6? What's the probability the numbers you roll are not all 6s? So each of these questions deals with an event in an experiment. And we will look at 2 methods to solve each question. Okay, so we're going to look at actually kind of figuring out all the different possible outcomes, and then also looking at this by computing it without having to look at all the possible outcomes. It's a little bit of a shortcut. Okay, so let's get some definitions down. It says, what is the sample space of the experiment? Roll a fair die 3 times. Well, the sample space of an experiment is the set of all possible outcomes of that experiment. So let's think about what the outcomes could be. You roll a die, and maybe the first time you get a 4, and then you get a 6, and then you get a 2. Okay, that's one outcome. Here's another outcome. We've got a 1, and a 1. Here's a third outcome, a 1, and a 2. And then a 5, a 6, and a 2. That's another outcome. And these are all different outcomes. So we want to consider the sample space would be all the possible outcomes. And there's some ways to figure out what these would be. One is to sort of systematically write them out. And then we'll also learn about the fundamental counting principle, which will help us understand exactly how many there are. So the sample space of this experiment is kind of nicely displayed here. You'll see we have the 1, 1, 1, the 1, 2, 1, the 1, 3, 1. We have all these different possible outcomes. Now, by counting, if we were just to count this, we would see that we have 216 outcomes. If you think each little block has 6 outcomes in it, and it's we see there 6 rows and 6 columns, and so it's really 6 by 6 by 6. The fundamental count, which is 216. The fundamental counting principle tells us the number of ways in which a series of successive things can occur is found by multiplying the number of ways each thing can occur. So when you roll a die one time, there are 6 different things that can happen. The number 1 can come up, the number 2 can come up, the number 3 can come up, the number 4 can come up, number 5 can come up, and finally the number 6 can come out. So the first time you roll it, you've got 6 things that can occur. And then the second time you roll it, 6 possible outcomes. And then the third time you roll it, 6 possible situations when you roll the die. So the total number is just going to be, based on this fundamental counting principle, 6 times 6 times 6, or 6 to the third, or 216. So what you're looking at in that grid is all the possible outcomes that you could get if you were to roll a die 3 times. 216 possible outcomes. Okay, an event is any collection or subset of the outcomes. And we're often interested in the probability of a particular event related to some outcomes. So, for example, in this question, they want to know how many ways can you get all ones? Well, if you look at the grid over here, you'll see that there's only one way to get all ones, right? I'll see if I can highlight it for you. The 1, the 1, and the 1. There's only one way out of 216 possible outcomes to get all ones. Okay. So in this situation, each outcome is equally likely to occur. And when this is the case, the probability of an event occurring, which is written the probability of the event, is, or this P of parenthesis E means probability of the event, is the number of outcomes in the event divided by the total number of outcomes in the sample space. So in this case, the probability of all ones, there's only one way that that can occur, and we're going to divide that by the total number of outcomes in the sample space, which is 216. So probability of all ones, number of ways to get all ones divided by the total number of outcomes, 1 divided by 216, which is about 0.00463. Now another way to solve this without having to be so deep and thoughtful in looking at the grid is to think of each toss as an event. Okay, so we're just going to toss it and that's an event. And we know that you could get a 1, a 2, a 3, a 4, a 5, or 6 as the picture shows. Because the outcome of the first roll does not affect the outcome of the second roll, and either of those will affect the outcome of the third roll, we say each toss of the die is an independent event. So the fact that you got a 2 on their first roll is not going to in any way affect whether you get a 2 on the second roll or the third roll or whatever. So for independent events, to find the probability that they all occur, you just multiply the probabilities that they each occur. Okay? So in this case, on a single roll of a die, there are 6 possible outcomes, just like the picture shows. And the probability that you roll a 1 is just going to be 1 out of 6, right? So the probability that you roll all ones when you roll a die 3 times is going to be the probability that you roll on a 1 on the first roll, and then a 1 on the second roll, and a 1 on the third roll. And so you would just multiply the probability of rolling a 1 times itself each 3 times. So we understand that the probability that you roll a 1 is 1/6, and then on the second roll, again 1/6, and on the third roll we want a 1, so it's 1 out of 6. You multiply those out, 1/6 to the third power. Simplified if you want, that's 1 out of 216, which is 0.00463. That's the same answer as we got before, but we didn't have to consider all the possibilities of sample space, which was a little bit mind-boggling. Okay, now let's find the probability that you roll all odd numbers. Okay, let's think about our sample space and what is that going to look like. Here's a set with all odds. Here's a set with all odds. Let's see, these are all odds. This row is going to be all, this whole column's out because it's got 2's in it. Now here we've got 1, 3, 1, 1, 3, 3, and 1, 3, 5. Those are all odds. This is out, and then you've got 1, 5, 1, 1, 5, 3, 1, 5, 5, and then this column is going to be all out because the middle number is a 6. Okay, and you kind of go like the 2's are going to be out. This whole thing is out because it's got 2's in it. The 3's have a possibility, so you can have the 3, 1, 1, the 3, 1, 3, the 3, 1, 5. This is, and then you could have the 3, 3, 1, all 3's, 3, 3, 5, 3, 5, 1, 3, 5, 3, 3, 5, 5. This is all out because of the 6. This whole row's out because of the 4's. And then the 5's. 5, 1, 1, 5, 1, 3, 5, 1, 5, 5, 3, 1. Have you stopped the video yet? Hopefully not. I'll just be real quick here. 5, 3, 3, 5, 3, 5, and then 5, 5, 1, 5, 5, 3, 5, 5, 5. Ugh, I'm exhausted. Okay, so let's see. 3, 6, 9. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sets of 3. So it looks like there's 27 ways that you can roll all odd numbers. We could have used the counting principle to figure out that a little bit easier. Besides having to just look at that, let's see how we would have done that. What we want to do is the probability of all odd is going to be the number of ways to get all odds divided by the total number. So in this case, we know the answer is 27 because those are the odds, all odds, divided by 216. But if you had just counted it, the number of ways to get all odds, when you roll a die, you have 3 odd numbers, 1, 3, and 5. And so that's what you would get on the first roll. The second roll you have 3 possibilities, and the third roll you have 3 possibilities. So you can see that 3 cubed is 27. So that's kind of a shortcut there of seeing that there's 27. You didn't have to count out your picture. So then the probability that they're all odd is 27 out of 216. 0.21 or 0.125. Now, let's use our multiplication rule and see if we can make this question a little bit easier. The probability you roll an odd number, when one time you're just rolling the dice, you would have to roll a 1, a 3, or a 5. So the probability that you roll an odd number would be 3 out of the 6 possible. You know, there's 3 numbers that are odd out of the total 6. Now, the probability in 3 rolls of a die that they're all odd would be, by the multiplication rule, the probability that they're odd times the probability that you roll an odd times the probability that you roll an odd. So that's 3, 6 times 3, 6 times 3, 6, 3, 6 to the third, which is 27 over 216, or 0.125. So that method was a lot easier than trying to look at the pictures and count it. So using the multiplication rule was definitely to our advantage there when we wanted to see what the probability of them all being odd, because it was very easy to think, okay, first roll odd, what are the chances? 3 out of 6. Second roll odd, what are the chances? 3 out of 6. Third roll odd, what are the chances? 3 out of 6. So let's look at another one. The probability that none of your rolls gets a number divisible by 3. Okay, so a number divisible by 3, when you are considering the numbers from 1 to 6, there's only 2 numbers that are divisible by 3. Those numbers are the number 3 and the number 6. Okay, so if you look at your sample space, you want none of your rolls to be divisible by 6. So that means none of your rolls gets a number that's divisible by 3. So when you look here, you can kind of see you're gonna take out anything with a 3 or a 6 in it. And so I'm kind of looking at what I'm going to take out now. So anything with a 3 or a 6 is going to get taken out. This whole, all of this column is out. Let's see. And then here we've got the 3 and the 6 are out. And then here, this is the 3 and the 6 are out. And then here, this whole guy is out. So, so all of these are out. And all of these are out. Let's see if we can kind of see a pattern. All of this is out, right? Because it's got a 3. And then all of this is out. And then some of these are out. Some of these are out. And you're going to get that same pattern. So maybe I can do this. Maybe you can kind of count it with me. You got 4 here, 4 here, 4 here, and 4 here. And so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 sets of 4, which is 64. Another way to think of it would just be to count it. If the numbers can't be divisible by 3, then what numbers would you have left? Well, the number 1, the number 2, the number 4, the number 5. So you have 4 numbers that are not divisible by 3, and you're going to roll the die 3 times. So 4 times 4 times 4, which is 64. So either way you think about it, you should, whether you look at the graph and try to count them, or whether you just use the counting principle, you see that if 4 numbers are not divisible by 3, so if you're going to roll it 3 times, you do 4 times 4 times 4, which is 64. So the probability that none of the rolls is divisible by 3 will be that 64 divided by 216, which is the 0.2963. Now the second method would be to just use the multiplication rule, and you can see how quick and fast this method is. So the probability that none of the rolls gets a number divisible by 3, you just think on the first roll, what is the probability it's not divisible by 3? Well, 4 numbers are not divisible by 3 out of the numbers from 1 to 6, so 4 out of 6. And then the second roll, not divisible by 3, that's 4 out of 6 again. And then the third roll, not divisible by 3, 4 out of 6 again. So you immediately get the answer with the multiplication rule, 0.2963. So definitely easier to think of with the multiplication rule. Okay, here's where it gets tricky. find the probability that you roll at least 1 6. Now I'll tell you that we're going to talk about now what's called the complement rule, and this is how we solve problems that deal with at least, probability problems that deal with at least. But let's look at our graph of the sample space and think about what it means. So to find the probability you roll at least 1 6. What I have highlighted in blue here is all the rolls that would not count. They don't have at least 1 6 in them. So how many is that? Well, there are, it's a set, it looks over here, if I'm looking at it, it looks like I have a set of 5. 1, 2, 3, 4, 5, and I have 1, 2, 3, 4, 5. So this is 25, and then I have that 5 times. 1, 2, 3, 4, 5. So I have 125 outcomes that do not have a 6 in them. So I would have to have 216 minus 125 outcomes that do have a 6 in them. So method 1 is to count it. You have 125 without a 6, 216 minus 125, which is 91 that have a 6, okay? So the probability that you have at least 1 6, that's going to be 91 out of your total sample space, which is 216. And that's a decimal approximation there. Now, just for a second, let's look at what is the probability. The probability that you have at least 1 6 is 91 out of 216. The probability that you have no 6, that's the blue ones. That was the 125 in the blue. So that's 125 out of 216. So it turns out that if you add those together, with a 6 and without a 6, you're going to get the entire sample space. So if you add the probabilities together, the probability of at least 1 6 and the probability of no 6, you actually get 1, because probabilities have to sum to 1. And you can use a tiny bit of algebra here and just move the probability of no 6 to the other side, and you would see that the probability of at least 1 6 is equal to the probability of is equal to 1 minus the probability of no 6. And the reason why this is important is because when we go to calculate probabilities where we want to know at least 1 of something, we want to use the multiplication rule and the fact that the probability of at least 1 is equal to 1 minus the probability of none. Because the probability of no 6 is easy to compute, right? Not a 6, not a 6, not a 6. Well, the probability that you don't roll a 6 is 5 out of 6 because, you didn't roll a 6, but you still have 5 other numbers that you could have rolled. So it's easy to figure that out. So this complement rule is very important for us to use. So the complement rule is the probability of an event happening at least once. So the probability of an event occurring is 1 minus the probability that it doesn't occur. Okay? So and this is our notation, the little c up top means A complement. So the probability of A is equal to 1 minus the probability of A complement. Because when you add the probability of A and its complement together, you get the entire sample space, or the entire, you get 1. So the probability of an event happening at least 1 is the probability of 1 minus the event does not happen. So the probability that you roll at least 1 6 is going to be equal to the probability of 1 minus equal to 1 minus the probability that you don't roll a 6. Now, it's easy to determine the probability that you don't roll a 6 because you don't roll it on the first time, you don't roll it on the second time, and you don't roll it on the third time. And to not roll it is 5 out of 6. So 1 minus 5 6 times 5 6 times 5 6. So 1 minus 5 6 to the third. If you compute that, it's 91 out of 216, or the 0.421296 that we got before. So you get the same answer. We didn't have that grid that we had to look at. Okay, find the probability that the numbers you roll are not all 6. Okay, well this is actually pretty easy to see graphically because there's only one way that they're all 6, way down there in the corner. So the probability that they're not all 6 would be all the other numbers, or I'm sorry, the outcomes that are not all 6 are all the other numbers. So in this case, the 215 that are not all 6. And so you would do 216 minus 1, which is 215. Only one way to get all 6, so 216 minus 1 equals 215 ways to get, in your event, not all 6. So the probability that they're not all 6 is going to be 215 out of 216. So pretty likely, 0.99537. So method 2 is trying to not have to use the sample space, seeing if we can think it through. The probability of not all 6, we can't just multiply to figure that out. But we understand that the probability of not all 6 is 1 minus the probability that they are all 6, because there's only one way that they can all be 6. And that probability is easy to compute, because the probability that you get a 6 is 1 out of 6. Because, you know, you're rolling a die, you've got 6 sides on the die, there's 1 6, the probability that you get a 6 would just be 1 out of 6. So the probability that they're not all 6 is going to be 1 minus the probability that they're all 6. And of course that probability is easy to compute. 1 minus 1 6 times 1 6 times 1 6, 1 minus 1 6 to the third. And then you see you do get the same answer as if you had thought about it with the sample space. The thing is, most of the time you're going to be using method 2, because coming up with a sample space is going to be impossible, or it could be that your events are not all equally likely and you can't even use method 1. So that's why we like to use method 2. Okay, I hope that helps you with the lesson.